Remember this, it's an Antikythera. An Antikythera is really an orrery. An orrery is a representation of the solar system with the sun at the centre, so it's called heliocentric. An Antikythera is a representation of the solar system where the Earth is at the centre, and it's called terracentric. Now there are two really remarkable things about this. The first one is that it was invented in 80 BC, so it's thousands of years old. And the second one is it contains something called an epicyclic gear. Now, epicyclic gear is where you have one gear where the second gear rotates around the one gear, a bit like a sun and a planet, and they're often called sun and planet gears, although I think they get their name from their original use in orreries and Antikytheras. Now, we wouldn't recognise a sun and planet gear as you know it today from this. It wasn't really until about 1588 when Agostino Romelli came up with something called the book wheel that we might begin to recognise it. And of course that developed into the famous James Watt sun and planet gear. And then of course we get the thing that we know, which is this thing, and this is, it's absolutely everywhere. Open up your drill and you'll find this. And we still call it the sun and planet, where we call the centre one the sun. The ones that go around the sun, the epicyclic gears, we call the planets, and it goes together where the sun goes in the centre of a carrier, the planets go there, and if we turn one, the others will turn in relation. So we can turn the sun, or we can turn the planets, and we get the epicyclic gear. You'll notice that the centre of this gear is rotating around the centre of that gear, which is what makes it epicyclic. Now, the number of planets spreads the forces, and you see any kind of planets. Normally you'll see about 3, and if we pop those together, we have ourselves a planet gear set so that it's like that. Now, what's good about these is you can get really good gear reductions in a compact space. But of course they have practical limitations on the size. You start making those planets too big, and they start bashing into each other. So the maximum, so the realistic, is about 10 to 1, and 4 to 1 to 8 to 1 gear ratios are much more common. Of course, what we would really like is in a very small package to have a very high gear reduction when we're looking at driving things slowly with lots of torque from a motor, for example. And now there are two ways to do that, and it's called compounding. One way is we can just stack them on top of each other so that each gear reduction adds on, actually it multiplies on, to get a whole stack of these where you get a massive gear reduction. And you find lots of people doing exactly that. For example, with this great model I found on Thingiverse from OT Vinter doing exactly that. Of course, there's another way of compounding gears. There's always more than one way of doing something. And another way is to stack the planets on top of each other where one planet is smaller than the other and they're rigidly fixed but on the same axle. And this is generally known as the Wolfrom gearbox, and it was invented by Ernst Wolfram in 1912. So if we're interested in the ratios of these things, it's actually not that difficult. If we think about the planet ratio, it's actually the number of teeth on the ring divided by the number of teeth on the sun. But of course, gear teeth are, well, they're a bit of an approximation really, because what we're really interested in is the circles that move over each other. So we can talk about the diameter of the ring and the diameter of the sun, and we'll get exactly the same answer as if we divide the number of teeth on the ring by the number of teeth on the sun. That will give us the planet ratio. Now you might think if we stack two planet gears on each other, they'd have the same effect. It would just be two of the same ratio, but it isn't. Something rather different happens. You'll notice we've got this little step inwards, because that's 12 teeth and that's 13 teeth. It gives us that little step, and that has a surprising impact. So to get hold of that impact, we have to think a little bit about levers. I mean, it's no surprise, is it? Because gears are really just levers that move in a circle. But a lever has three main components, one of which we tend to forget. The two main components are the fulcrum and the lever rod itself, and we tend to think about how it's positioned to what forces are going to be applied and resultant. But of course, we are standing on a lump of ground, and that ground is actually really important because you have to push against something. So when we introduce this little step like that, and we hold the ring and drive this bottom, that top one is acting like a lever, where this is acting like the ground. So it's no longer like stacking them up, which we saw before. It's very different in that we've got this lever operation going on. So the gear ratio of a Wolfram set actually is the gear ratio of the initial planet set multiplied by that lever effect. So to put this together, there's our planet carrier, and we pop the planets on with the larger gears at the bottom before we turn it round. Then there's this gear. This is just the idler sun gear. It doesn't drive anything particularly, it's just there to space everything out and transmit some of the forces. This is the driven sun, and it goes in there like that. It drives the small planets. The small planets are attached to the larger planets. The larger planets now operate under a lever effect, and you can see that step's tiny. So that's going to be a pretty strong lever. Having a strong lever there means that we get a huge gear ratio from something that is very compact. So the sun, the planet and its carrier go into the ring just like in a normal planetary gear set. Remember, this is going to be the ground ring, so to speak, and that's the one we hold. This is the output ring, it's the driven ring, and that fits on top of there on that upper set of planets. Right, I've put a handle on it and a bit of black tape, and we'll give it a turn and see what happens. That's awesome. There you go. There we are, Wolfrom Drive. Now, invented in 1912, you might wonder why it didn't catch on, and there are a couple of good reasons for that. One of the things is these gears, these planet gears. Now, I must admit, I did cheat a little bit in that I left enough slack to make sure that it would work, but if you want those gears meshing properly, you have to index the top and the bottom. You have to match them against each other. Otherwise, it'll jam up and snatch and doesn't work very well, and that's a bit of a problem. The second one is it's limited. It's limited to the tooth size, because remember, the tooth is effectively the lever that's doing the job. The smaller you can make that tooth, the better your lever, the higher the gear ratio. But there's a limit when you're doing something like this to how small you can actually make it. So the Wolfrom Drive really is a little bit of an oddity, and a lot of people are investigating it. And those two challenges of indexing and tooth size that can be overcome would be, well, quite a drive indeed. Anyway, I will put these on Thingiverse should anybody actually want to play around with it and to get better matching on those top and bottom planets. I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.